Imagine a volcanic eruption so powerful that its effects could be felt thousands of miles away, penetrating the Earth's crust to a depth of 5 kilometers. This isn't science fiction. It's exactly what happened in 2022 when the Hunga Ha'apai volcano erupted in the South Pacific, sending seismic waves deep into the ground in Alaska. Ken McPherson, a scientist at the University of Alaska Fairbanks Geophysical Institute, along with his colleagues, seized this rare opportunity to study how these atmospheric waves interacted with the ground. By analyzing the coupling between atmospheric pressure waves and the Earth's surface, they aim to understand the speed at which seismic waves travel through Alaska's upper crust. To put this in perspective, imagine blowing on the surface of a bowl of Jell-O versus a pan of brownie batter. The Jell-O would jiggle noticeably, while the brownies would barely move due to their stiffness. Similarly, the properties of subsurface materials, such as their hardness, affect how seismic waves propagate. By comparing the strength of the incoming pressure waves with the resulting seismic waves, researchers can infer important characteristics of the subsurface. The pressure waves from Hunga have given us invaluable insights into how seismic waves behave in Alaska, McPherson explained. His findings, which delve into seismic velocities at depths of 30 meters, 2 kilometers, and 5 kilometers, have been published in Seismica, https://seismica.library.mcgill.ca/article/view1557. The eruption of Hunga Ha'apai on January 15, 2022, was one of the most significant volcanic events in recent history. Located about 6,000 miles from Alaska, the eruption generated atmospheric waves that were the largest recorded since the 1883 Krakatau eruption. This was an unprecedented explosion in the modern era of instrumentation, McPherson noted. The fact that these pressure waves could shake Alaska 6,000 miles away is truly remarkable. A network of 150 barometers, infrasound sensors, and seismometers in Alaska captured the data used in McPherson's research. Gaining information about the subsurface at a depth of 5 kilometers through air-to-ground coupling is quite rare. Typically, seismic waves produced by this coupling have a shorter wavelength, unless the energy source is extraordinarily powerful. The sheer magnitude of the Hunga eruption meant that the pressure waves traveling such a long distance to Alaska were still strong enough to cause significant ground movement, making them perfect for our study, McPherson said. But how do atmospheric pressure waves actually shake the ground? When powerful pressure waves from a volcanic eruption or explosion travel through the atmosphere, they cause rapid changes in air pressure. Upon reaching the ground, these waves push and pull on the surface, transferring energy into the Earth's interior through a process known as air-to-ground coupling. This transfer of energy follows Newton's second law, which states that an applied force can move particles by overcoming their inertia. As these particles move, they generate seismic waves that carry both kinetic and elastic energy. Understanding seismic wave velocities is crucial for seismic hazard analysis. For example, if a wave traveling through hard, deep material suddenly encounters softer material, it will slow down, but the energy remains constant. This results in larger amplitudes and more intense shaking. Knowing the velocities of the upper crust helps us predict and mitigate seismic hazards more effectively, McPherson emphasized. It also aids network operators like the Alaska Earthquake Center in improving earthquake location accuracy. McPherson's research has broader applications in tomography, a technique used by seismologists to create 3D images of the Earth's interior. By understanding how seismic waves travel through different materials, scientists can map the deep subsurface and identify variations in properties like density and velocity. For accurate tomography, we need to account for the differences in velocity between the upper crust and deeper layers. Knowing the crustal velocities allows us to apply corrections that enhance the quality of our images over large areas, McPherson added. The research team, including co-authors David Fee, Stefan Awender, Bryant Chow, Julianne Colwell, Sam Delamere, and Matthew Haney, continues to explore the implications of their findings. Their work not only sheds light on the unique properties of Alaska's subsurface, but also contributes to our broader understanding of seismic activity and Earth's internal structure. And this is the part most people miss. The impact of distant volcanic eruptions on far-off regions is a fascinating and often overlooked aspect of geophysics. How do you feel about the idea that a volcanic eruption in the South Pacific can influence the ground beneath your feet in Alaska? Share your thoughts in the comments below.